All righty, we're still slogging on through this chapter. Has anyone looked at the assignment yet? You're going to want to.
I don't want to.
No, you're going to want to.
I was like, I won't, if I.
You don't want to save this till Thursday night. Ivy will have the key, so she should be able to help with some stuff, but you're going to want to get it started. All righty, so we were talking about electric force. Now we're on to electric field. Okay, so remember, our electric force is essentially, we're going to have Coulomb's constant. QQ over R squared. But then we found out, hopefully by reading the textbook, that electric field is electric force divided by charge Q. So that means we're going to get 1 over Q. And so what that ends up giving us is our electric field. Where that Q prime is now the entire charge that we're observing. So that's going to be big Q over R squared. And so, so that means that as we start to understand it better, electric force is going to be the interaction of some charge Q coming into contact with the electric field of another charge. So that ends up leading us to we've been doing this a little bit and talking about it along the way. So this is something we're going to be using quite a bit. You know, we kind of use it on forces. I guess you could say it applies more to electric field because we're trying to figure out the field at a specific point. But it's the same mechanism for forces, for fields. It's called superposition. So what we imagine is we're going to have some point in space. Then around that point, we'll see, we'll do a positive. And a positive. And then do a negative. And a positive. Okay, so let's see, we'll call this Q1, Q2, Q4. That's Q3. We could say negative Q3. So when we're looking at these, electric field vectors will act along which direction? Well, so out of positive into negative, but if we're looking at these individual charges in a point P in space, do you remember what we said about the way that whether the vectors are pointing towards or away the charge? They what? How do they interact? Along what direction? the line that connects the charge to the point. Close enough. Okay, so do we want to start saying, okay, so again, electric field vectors are going to point away from positive and towards negative. So for this first one here, we're going to try to. We're going to try to go along that line, close as we can get, away from the charge. We're going to do the same for charge 2. Charge 3 is negative, so it's going to point towards the charge, and then of course we're going to point away from charge 4. And so what we're going to have is we're going to have that's E2, that one's E1. And so of course these are all at some point in space P. So we have all these different interacting electric fields at that point. So then the question becomes, what is the electric field, the superposition, the total electric field at that point? So the electric field at point P is going to be the vector sum of all of the different electric fields going through that point. In this case, it's going to be I equals 1 through 4. So this is the principle of superposition. So again, here we only have 4 point charges, but we could have an infinite number. I can give you a problem that has 20 point charges. Yeah, you could solve that one by hand, but it'd take a while. So when we say superposition, this is what we mean. And so then from there, you have to figure out the vector components of each one of those, do the vector sum. Then you might find the magnitude and the direction of the total electric field. All right. So let's try to find the magnitude and direction of the electric field at point B due to charges. Well, let's see, and I'll give you the figure here. So make more sense after that. So Q1 will be 0.040 microcoulombs, 0.010, Q2 is 0.010 microcoulombs. Charge Q1 is at the origin of a, oh, so you're supposed to be able to draw it from this. That's why I wrote it that way. Okay, so then point P is at x equals 1.5 meters. So what would this look like? We have our y-axis. We have our x-axis, so Q1 going to be at the origin. Let's see, Q2 is at 0.3 meters. And then point P is going to be way out here at 1.5 meters. Alrighty, so let's see here. We got there's 0.3 meters. And so then if that whole distance is 1.5 meters, what is the distance we haven't marked? 1.2. So we have everything marked the way we need it. And then let's see. Find the magnitude and direction of the electric field at point P. Okay, well, both of these are positive charges. So at point P, they're both, you don't really have to draw them in, but they're both going to be vectors pointing away. So they're both going to be pointed that way. All righty, so do you remember? Let's start looking for, let's look for the electric field one. Okay. One, KE, Q1, over R, 1 to P squared. Nope, that's not quite right. It's Newton's meter squared, Coulomb squared. There we go. Then our charge one is 0.40 microcoulombs. How are we going to put that into the problem? Yep. And then our distance from 1 to P is going to be 1.50 meters squared. When you calculate this, you're going to get 160 newtons per coulomb. But since both of those field vectors are going to point in the same direction along the positive x-axis, no, not 1 point. So what, 160 newtons per coulomb, I hat. Okay, what about electric field 2? E2 is, of course, going to be so again, Q2, the distance from 2 to P squared. And what is Q2? 0.010, 10 to the negative 6 coulombs. Over 1.22 meters squared. That will end up giving you 62.4 newtons per coulomb. And then, of course, this points in the same direction as E1. So they're both I hat vectors. Okay. the electric field at P will be E1 plus E2. So that's just going to be because there are no Y components. And you end up right at about 222 newtons per coulomb I hat. So in this case, the magnitude is easy because since everything is in that positive I hat direction, your E is just going to be 222 newtons per coulomb. In the direction, we don't have to find theta because again, this one lies right along the x-axis. Okay. So this is 222 newtons per coulomb in the positive x direction. So that's superposition about as straightforward as a manner as it gets. But what was it the guy on TV used to say? But wait, there's more. Okay. 2-point charges are at the lower corners of a rectangle. Q1 will be negative 1.0 microcoulombs at the lower left corner. Q2 is 6 microcoulombs at the lower right corner. The long horizontal side of the rectangle between Q1 and Q2 is 0.5 meters, while the short vertical side of the rectangle is 0.2 meters. For a point P at the top left corner of the rectangle, what is the electric field at P and what is the acceleration of a proton at point P? Okay, so let's just start with, think it'll cooperate today? Yep. So we have our rectangle. Okay, so we are going to want, okay, so that's negative Q. That's positive Q. And then point P going to be right there. Okay, now the line connecting P to Q1 is fairly obvious. What about the line connecting Q2 to P? Yeah, so it's going to be the diagonal of the rectangle. So we're going to need that. Okay. We'll just call that distance D for right now. All righty, so let's think about the way that our vectors are going to point. There's electric field 1, because it goes from point P towards the negative charge. And then Q2 is a positive charge. So E2 will point in that direction. And then it's also going to help us to find angle theta. Why do you think that is? Right, because we're going to need the components of E2. And if we think about putting an XY axis there, that angle will also be theta. Okay, so let's start figuring these field vectors out. So E1. Okay, so it's magnitude of -1 microcoulombs. So that's 1 times 10 to the -6 coulombs over, and that's going to go 0.20 meters squared. That will calculate out to be a magnitude of 2.25 times 10 to the 5th newtons per coulomb, and then of course it's going to become should be an easy explanation, but tell me why the vector ended up written like that. So it's on the y-axis going straight down. Now we have to find E2, and we're going to need two components. And we said that that angle's theta. So we need to find EX and EY. Okay, so there's a couple of things we're going to need here. First off, we have to know the distance between point 2 or Q2 and point P. All right. So Liam said it earlier, we're going to use what? Yep. Have any of you contacted your high school math teachers back yet and said, I apologize, I now know where I'm going to use it? Some of you need to. Okay, so D is going to end up being so we solve this, D is going to be 0.539 meters. Okay. And then we could use almost any trig function to figure out theta, because what that again, that's our 0.50 meters. That side 0.20 meters. I used cosine. And you get a theta of about 21.9 degrees. Now we're ready to figure out our components. Well, kind of. We need our magnitude for E2 first. And so Q2, what is that? It's 6 microcoulombs. And then, of course, the R distance there is just D. So that's going to be 0.539 meters squared. And that's going to give us 1.86 times 10 to the fifth newtons per coulomb. Now, all these numbers we found, we can use to find the components of E2. How much more space do I have? Oh, I'm doing good. Okay. So, looking at this, EX is going to use what trig function? Cosine, and then E2Y will be sine. Alrighty, that's going to be 1.86. And for Coulomb cosine, 21.9 degrees. Going to give you 1.73 newtons per Coulomb. Is it going to stay like that? Nope. It's going to become negative because EX is pointing in the negative X direction. Okay, E2Y. And again, the great thing is, if you already know which trig functions each one's going to take, great. But if you find EX is cosine, then EY automatically has to be sine. It's just they have to be the opposite of each other. So what? That's going to end up giving you 6.94 10 to the fourth newtons per coulomb. And that one stays positive because EY points up. So now we want to write this in our favorite way ever. Yep. Okay. Because we have to have two vectors in order to add these together. All righty. So the total field And so we're just going to plug in our numbers once we get there. And let's see. So E1 has no X component, so that's 0. And if you're minus 1.73 to the 5th newtons per coulomb, that's your new I hat. And then your EY. Your E1Y is going to be your negative 2.25 10 to the 5th newtons per coulomb plus 6.94 10 to the 4th newtons per coulomb. And that's your new J hat. The point P is going to become negative 1.73 for the I hat. And then minus 1.56 10 to the 5th for your J hat. So we have a nice third quadrant vector. Nope. Because you have a negative 2.25 10 to the 5th and a positive 6.94 10 to the 4th. That second one, even though positive, is a whole order of magnitude smaller than the first one. So that would be like 0.694 times 10 to the 5th. All righty. So that's the first thing we had to find. Then we had to find the magnitude. So we just used the magnitude equation. This is going to give you a magnitude of 2.33 times 10 to the 5th. And I would definitely suggest practicing with your calculators because especially with high energy, these numbers take a lot of typing. And you want to make sure that you're getting your calculator to give you the correct answer. Okay, the last thing we wanted to figure out was the direction, which, okay. Well, at least for part A. Oh, part B is this whole thing over again, except it's the force on a proton. You find out that these tiny, tiny, tiny electric charges accelerate a proton to near the speed of light in just a few seconds. Okay, so I just called this angle phi. So that's our inverse tangent of EY over EX. Now there is a faster way you could write this out. What could I neglect? The 10 to the 5th, I could just get rid of it. They're both on the same order of magnitude, so I could just do the 1.56 over the 1.73. Phi is going to come out to be 42 degrees. So this is a smaller angle, so if the vector was halfway through the quadrant, it'd be at 45 degrees. We know this is a smaller angle. We also know magnitude-wise, X is slightly larger than Y, and this is a positive angle. So this is going to have to be the positive angle counterclockwise, but for you, it's this way, counterclockwise down from the negative X-axis into the third quadrant. So what that would look like is, let me go ahead, I don't want to draw it again, so. Let me bring this here. And what it would look like is we would have well, it's close enough. That'd be your angle phi. And that's your electric field at P. All righty. So part B. Let's remind ourselves of what that says. What is the electric, so we found that. What is the acceleration of a proton at point P? So here's a question. Do I have to do all this over again for place a proton at point P, use E as the elementary charge, and do this all over again for forces? Nope. What can I do? It's going to be the same electric fields. How do I turn an electric field into an electric force? Force equals what? Yep. So it's going to be your charge Q. For us, that's going to be a proton multiplied by that electric field. Now, of course, fun. You notice that I did continue to use vector notation, so that's going to come into play. Now, what else does force equal? We're trying to find the acceleration of this proton. What else does force equal? Mass times acceleration. So, mass of your proton, acceleration of your proton. Well, let's go ahead and E, the elementary charge, times your electric field. Your acceleration then. Okay, do you remember when we were doing vectors and we did multiplication of a scalar into a vector and it's distributive? What does distributive mean again? Yeah, so if I multiply my vector by 3, I just multiply each component by 3. And so this is going to mean that I'm going to have E over the mass of a proton the X component of the electric field plus E over the mass of a proton. And that'll give me my I hat and J hat for the acceleration of the proton. Okay, these are some large numbers. Okay, the elementary charge, 1.602 times 10 to the negative 19th coulombs. Mass of a proton, 1.673. 10 to the negative 27th kilograms. And then, of course, our X component, negative 1.73. 10 to the fifth newtons per coulomb. That's your I hat. Plus, I don't want to write it again. And then what? Get a negative 1.56. 10 to the fifth newtons per coulomb. And that's my J hat component. My acceleration comes out to be negative 1.66 times 10 to the 13th meters per second squared. So that's my I hat component. You think you could get coulombs over kilograms times newtons over coulombs and get meters per second squared? Do you not remember freshman year when we did dimensional analysis? Think about it. Coulomb over kilogram, Newton over Coulomb. Well, those two are gone. That's Newton over kilogram. And what is the Newton? Kilogram, meters per second squared over kilograms. Meters per second squared. Sometimes you want to double check to make sure you're getting the right units. If you've done a bunch of math and you end up with wonky units, you have the wrong answer. So our other component for our acceleration will end up being 1.49 times 10 to the 13th meters per second squared. And I'll let you plug in these numbers because, of course, our magnitude, ax squared plus ay squared, 1/2. When you plug in your numbers, you should get about 2.23 times 10 to the 13th meters per second squared. In what direction? The direction should be very, very straightforward. The exact same as the electric field. So remember, positive charges are always going to go in the direction of the electric field. Negative charges will go anti-parallel to the electric field. So if you think about this, have any of you ever fallen off something high up and it hurt when you hit the ground? Okay, well, your acceleration is 9.8 meters per second squared, and you feel how hard you hit. This is on the order of 10 to the 13th meters per second squared. How fast would you be going if you just fell off your bed by the time you hit the floor? You'd be a puddle, just falling off your bed. This is more acceleration than Jupiter has. So electric fields, magnetic fields, very, very, very powerful. This is why, for example, you throw a proton in there, it's going to get near the speed of light within a few, like, maybe even, I don't know, large estimation, a few seconds, but you would go very fast in a very quick time. Okay, so that was a fun problem. So I want to, with our last 2 minutes, I do want to talk about field lines. So as we've been talking about, whenever you're working with electric fields, based off the shapes of your positive and negative, that's going to dictate your electric field. So you notice like the two plates, that's going to be a capacitor. You have a straight field between the two of them. You see the field between the 2 point charges. And then, of course, you can see the mixture of a point charge and a plate. So it starts to come out in a spherical pattern, ends up in the straight pattern as it reaches the plate. And then, so of course, we also have repulsive fields and attractive fields. So the repulsive fields are always, theoretically, they're going to have a node right in the center. What do I mean by a node? A region of what? No charge. So in reality, there's always a little bit of charge in there, but still, this is what we're looking at. And keep in mind, your electric field at every single point along the field line will be a tangent to the field line, okay? Where you would end up having where each one of those is going to have a positive and negative component. So yeah, your electric field vector is going to be tangent to the electric field line at every single point. Okay, so we'll go ahead and end there. Pick this up on Wednesday. Start getting used to the concept of superposition. And get started on that. Get started on the assignment. You are not going to want to wait till the last minute. No, not yet. The next one will.